In this video, we will learn about function transformations. We will begin with translations in both the horizontal and vertical directions. After that, we will move on to reflections across the x-axis and the y-axis. We will also learn how to stretch and compress functions vertically and horizontally. Finally, we shall explore how different transformations can be combined. If you're unfamiliar with functions, I recommend watching the previous videos in this series, especially the first introductory video. The playlist is linked in the card in the top right corner and in the video description below. Let's say we have this quadratic function. Its graph looks like this. We will make a copy of the quadratic and add a constant of 3. This translates the function vertically by 3 units. Simplifying the orange equation gives us this form. Graphically, the curve moves upward by 3 units. If we draw a vertical green line between the curves, its length is exactly 3 units. No matter which x value we choose for the green line, that distance remains constant. In general, if the original blue function is f, the translated orange function is f plus a, where a represents the amount of vertical translation. The translation vector can therefore be written in this general form. Let's adjust the axes slightly. This time, we will translate the curve horizontally by 3 units to the right. In the original equation, every x in the blue equation is replaced by x minus 3, because the translation is 3 units to the right. The green line is 3 units long, showing that corresponding points on the blue and orange curves are always 3 units apart. In this case, the translation vector is as follows. If the original function is f, the general form of the horizontally translated function is f of x minus a. The corresponding translation vector is a0. Now let's consider a different quadratic and adjust the axes slightly. Suppose we replace each x with x minus 2. What kind of transformation does this produce? As we have just seen, it's a horizontal translation. The orange graph is simply the blue graph translated 2 units to the right. Next, let's consider a square root function. Its graph looks like this. This time, we will translate the curve both horizontally and vertically. For translations, it does not matter which of these two movements we perform first. Let's begin with the horizontal translation, which means replacing x with x plus 5. Visually, the graph shifts 5 units to the left. For the vertical translation, we add 3 to the function, and this moves the curve upward by 3 units. We can then simplify the orange equation into this form. Now let's look at another quadratic. Its graph is shown here. Suppose we reflect it across the x-axis. For example, when x equals 4, the y value of the blue curve is 9. At the same x value, the y value of the orange curve is negative 9. For any input, the two y values have the same magnitude but opposite signs. The orange function is therefore closely related to the blue one, except that the entire expression is multiplied by -1. In general, if the original function is f, its reflection across the x-axis is gonna be -f. Let's adjust the axes once again and color the portion of the curve to the left of the y-axis green. This time, we reflect the curve across the y-axis. The blue section reflects onto the other green section. This means that if the function has a particular y value at x equals 4, its reflection has exactly the same y value at x equals -4. The same relationship holds for every pair of opposite x values. In the equation, this reflection is produced by replacing every x with -x. More generally, if the original function is f of x, its reflection across the y-axis is f of -x. Now let's examine yet another quadratic. Its graph looks like this. We make a copy of the equation and multiply the entire right-hand side by 2. And this produces the orange curve shown over here. At x equals 4, the orange dashed line is twice as long as the blue dashed line. In other words, the magnitude of the orange y value is twice that of the blue y value. This happens because the original function was multiplied by 2. The same relationship holds for every x value, regardless of whether the corresponding y value is positive or negative. In general, if the original function is f, the vertically scaled function is a times f, where a is the scale factor. In this example, a is equal to 2. Let's modify the axes slightly. This time, we replace every x with 2x. What effect does this have? The orange curve looks like this. The graph has been compressed horizontally by a factor of 1/2. For the same y value, the blue point is twice as far away from the y-axis as the corresponding orange point. This occurs because the coefficient of x inside the function is 2. The relationship holds throughout both curves. In general, replacing x with ax gives a horizontal scale factor of 1 divided by the magnitude of a. Since a equals 2 here, the horizontal scale factor is 1/2. Now let's look at another quadratic, this time with an inverted U-shape. We multiply the entire right-hand side by 4 and simplify the expression into this form. As we have learned, this is a vertical stretch by a factor of 4. In the previous example of vertical stretching, the factor was 2. Here, the transformed output is 4 times the original output. As a result, the dash distance from the blue curve to the orange curve is 3 times the length of the blue dashed line. This relationship is true for every x value. That's enough quadratics for now. Let's work with a piecewise function instead. Suppose the transformed function is required to have this equation. This expression combines 2 transformations. First, the green graph represents a vertical stretch by a factor of 2. We then translate it downwards by 3 units to obtain the final orange curve. Now consider an important question. If we perform the translation first and the stretch second, would we obtain the same result? Let's find out. We begin by translating the blue function downward by 3 units to produce the red graph. Next, we stretch the red curve vertically by a factor of 2, giving us the purple graph. The orange and purple results don't match, so we must be careful about the order in which transformations are applied. In terms of the equations, the red curve represents the downward translation, while the purple curve includes the subsequent stretch. Comparing the orange and purple equations also makes it clear that the two results are different. For our final example, let's begin with a simple squared function. We already know what this graph looks like. Suppose a sequence of 2 horizontal transformations changes the blue function into the orange one. What exactly are those 2 transformations? Can you work them out? First, we translate the graph 4 units to the right to obtain the green curve. We then apply a horizontal scale factor of 0.5, compressing the graph to produce the red curve. The equation of the green curve is shown here, followed by the equation of the red curve. We can identify these equations using what we have learned about the effect of each transformation. But is this the only valid sequence of 2 transformations? What if we apply the horizontal scaling first and translate afterward? This time, the required translation is 2 units rather than 4. Scaling the blue curve gives us the red one. Translating that red curve 2 units to the right then superimposes the green result on the target orange curve. Therefore, this is also a valid sequence of transformations. The red equation is shown first, followed by the green equation. We have now mastered function transformations. Please consider liking, commenting, and subscribing to support the work that goes into making these videos. Stay tuned for future videos on functions and many other topics, some of which should be on your screen right now.